Have you ever noticed how a second can feel like an eternity, or vanish in the blink of an eye? Time seems so obvious, so fundamental to our existence, that we rarely stop to question it. It's in the tick-tock of the clock on the wall, the date we mark on the calendar, the rhythm of our own heart. But the more we try to understand it, the more it reveals itself as an enigma, a mirage that slips through the fingers of our comprehension. What we call a second is, in reality, a purely human invention, a ruler we created to try and measure an invisible river, a way to give shape and order to something that may not even exist in the way we imagine. It's a collective agreement, a convention that allows us to organize our lives, set appointments, and build technologies. But it is not time. It is merely our shadow cast upon the mystery of becoming. Today, we will embark on a journey beyond the hands of the clock and the pages of the calendar. We are going to explore time as it truly presents itself, not the time of clocks, but the time of our perceptions, the time of quantum physics and relativity, and the time of the profound questions that even the most brilliant scientists of our age still don't know how to answer. Prepare to discover that the reality of time is far stranger, more flexible, and more mysterious than any science fiction could ever dream. How much time really fits into 1 second? The question seems simple, almost childlike. The answer, however, opens an abyss beneath our feet. In 1 second, there can be infinity or absolutely nothing at all. Think of the experience of waiting for the results of an important medical exam. Each second drags on, heavy, dense, laden with anxiety and expectation. A minute transforms into a small eternity. Now remember a moment of pure joy, a genuine laugh with friends, a tight hug from someone you love. Where did the time go? Minutes, perhaps hours, disappeared in an instant, consumed by the intensity of the emotion. Our notion of time is not a universal constant. It's a subjective construction, an illusion woven by our own brain. The sensation of duration stretches and contracts like a rubber band, molded by our emotions, our level of attention, the novelty of the experience, and our expectations. The brain, deep down, is a notoriously imperfect and biased timekeeper. It doesn't register time with the precision of a Swiss chronometer. Instead, it creates a temporal narrative based on the amount of information it processes. When we are in a new or dangerous situation, like a scare or an accident, the brain enters a high-definition mode, capturing every detail. Later, when accessing this dense and rich memory, we have the impression that the event lasted much longer than it actually did. It's the famous slow-motion effect that people report in moments of crisis. On the other hand, routine, repetition, causes the brain to operate in an energy-saving mode. Days merge into one another, and entire weeks can pass feeling like just a blur. Time, for our consciousness, does not flow uniformly. It is a deeply personal experience, a melody whose rhythm is dictated by the complex orchestra of our neurons, hormones, and memories. This subjectivity reveals a disconcerting truth. Perhaps we have never experienced real time, only our interpretation of it. Now let's broaden our gaze and see how the meaning of a second transforms radically depending on the perspective. For an Olympic athlete in the 100-meter dash final, a millisecond, 1,000th of a second, is not an abstraction. It is the tangible difference between eternal glory and oblivion, between the gold medal and 4th place. In this universe of peak performance, time is sliced into portions so infinitesimal that they become the battlefield where destinies are decided. Every movement, every muscle contraction is timed and analyzed with a precision that borders on the absurd. For this athlete, a second is a vast landscape of opportunities and decisions. For an ordinary observer sitting in the stands, that same millisecond is completely imperceptible, a fragment of reality that passes without a trace in their consciousness. What does this reveal to us? That time is not an absolute entity with an intrinsic and universal value. It is relative to the context, the mental state, and, crucially, the purpose. For a geologist studying the formation of a mountain range, 1,000,000 years might be a reasonably short period of time. For an astronomer observing the light from a distant galaxy, the now is a window into a past of billions of years. For a programmer of high-frequency financial trading systems, a nanosecond, 1/1000th of a second, can mean the difference between millions in profit or a catastrophic loss. And for a fly, whose life lasts only a few days and whose nervous system processes visual information much faster than ours, We humans move as if in slow motion. Each of these examples shatters our intuition of a single shared time. Time is not a neutral stage where events unfold. It is an active participant whose form and value are defined by the nature of the observer and the event being observed. The athlete's second is not the same as the geologist's second, which is not the same as the fly's second. Each inhabits its own temporal reality. The idea of a universal now, a present moment that we all share simultaneously, begins to unravel. Our intuition tells us that a clock measures time. That is its function, its reason for being. But this is one of the biggest and most ingrained illusions we accept without question. No clock, from the most ancient sundial to the most sophisticated atomic clock, has ever measured time. What it does is something much simpler, and at the same time, much more ingenious. It counts repetitive events. A clock is, essentially, a cycle counter. Let's think about its ancestors. The sundial did not measure time. It tracked the regular change in the position of the shadow cast by the sun. The clepsydra, or water clock, did not measure time. It counted the steady dripping of water from one container to another. The pendulum clock, a revolution in precision, did not measure time. It counted the rhythmic oscillations of a suspended weight. Each of these instruments is based on a physical phenomenon that repeats with reasonable predictability. The advancement of clock technology was, in fact, the search for an ever more stable and rapid oscillator. The pendulum was replaced by the vibration of a tuning fork, which in turn was replaced by the vibration of a quartz crystal when subjected to an electric current. The quartz clock, which is on your wrist or in your phone, counts these vibrations, precisely 32,768 per second. We then take this count of physical events and call it time. Time is a deduced quantity, an inference we make from observing change. It's like trying to understand music by only counting the beats of a metronome. The metronome provides the rhythm, the structure, but it is not the music. Likewise, the clock gives us a structure, a ruler, but it is not time. It is a translator, a device that converts the physical process of change into a numerical format that we can understand and use to synchronize our lives. This realization is fundamental. We do not measure time itself, we measure movement, vibration, decay, and from there we construct the idea of a temporal flow. If the search for a perfect clock is the search for a perfect oscillator, modern science has found it in the heart of the atom. Here we enter the realm of mind-boggling precision, where our concept of a second gets its official and universal definition. Today, the second is no longer defined by the Earth's movement or the swing of a pendulum. It is defined with an accuracy that defies imagination. A second is, by international convention, the duration of exactly 9,192,631,170, 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. It's a complex definition, but the idea behind it is the same as always. We are counting cycles. In this case, the incredibly fast and stable vibrations of a specific atom. The atomic clock which performs this count is a marvel of engineering. It is so precise that it would take over 100 million years to gain or lose a single second. This precision is not a mere academic exercise. It is the invisible backbone of our entire technological civilization. The Global Positioning System, GPS, which guides our cars and planes, works by comparing time signals from multiple satellites. Without the precision of the atomic clocks aboard these satellites, the system would accumulate errors of kilometers in a single day. The internet, global financial transactions, power grids, telecommunications, all depend on perfect global synchronization, a universal pulse dictated by these cesium atoms vibrating in laboratories around the world. It is fascinating and paradoxical. We have built a global system that depends entirely on a count of atomic oscillations. We have defined our unit of time based on the behavior of matter at its most fundamental level. And yet, even with this incredibly precise definition, the original question remains untouched, unanswered. We have managed to create the most exact ruler ever conceived, but we still don't know what exactly we are measuring. What is the time that this ruler supposedly measures? Science has given us the how, but the what remains a profound mystery. And here we arrive at the heart of the measurement paradox, a philosophical turn that challenges the very nature of our scientific inquiry. Even with the precision of atomic clocks, we only count what happens, the events, the vibrations. We do not measure time itself. Time, as an independent entity, seems to escape any instrument. Imagine you want to measure the speed of a car. You measure the distance it traveled and divide by the time it took. But how do you measure time itself? You use a clock. And what does the clock do? It counts other events. We fall into a circular reasoning. We measure change in relation to another change. We measure the Earth's rotation in relation to the vibration of a cesium atom. We measure a person's aging in relation to the Earth's rotation. We are always comparing processes, never isolating the essence of time. The second is not a thing that exists in nature, like a rock or an electron. It is an idea, a concept, a unit that we project onto the universe to make it make sense to us. Physics is spectacularly successful at measuring durations, intervals between events, but the continuous flow we call time remains a ghost in the machine. There is no timeometer that we can point at the universe and get a reading of time. It has no mass, no charge. It doesn't interact in a way that we can capture it directly. It is the backdrop for all the equations of classical physics, the parameter t, which marches forward inexorably, but its physical nature is unknown. It's as if we were trying to catch fog with a net. We can describe its effects, its humidity, its appearance, but we cannot hold the fog itself. With time, it's the same. We measure the shadows it casts, aging, movement, change, but the thing casting the shadow remains invisible, perhaps even non-existent as a separate entity. Our quest for the nature of time now takes us to the extreme limit of the measurable, to the frontiers of reality itself as we know it. If a second can be divided into milliseconds, microseconds, and nanoseconds, is there a limit? Is there an instant of time so short that it cannot be divided? The answer, according to theoretical physics, seems to be yes. Welcome to Planck time. Named after the physicist Max Planck, one of the fathers of quantum mechanics, Planck time represents the smallest interval of time that has any physical meaning. Its value is approximately 5.39 times 10 to the power of minus 44 seconds. It is a number so ridiculously small that it's almost impossible to visualize. To give you an idea, there are more Planck times in a single second than all the seconds that have passed since the Big Bang, 13.8 billion years ago. Planck time is not just a small number, it is a fundamental limit. It is believed that below this scale, our concepts of time and space simply cease to function. Classical physics, and even Einstein's relativity, which describe a smooth and continuous space-time, break down completely. At this ultra-microscopic scale, space-time would become a kind of quantum foam, a bubbling probabilistic chaos where before and after lose their meaning. It is the minimum tick of the universe's clock, the highest resolution of reality. Just as a digital image is composed of pixels and cannot be infinitely magnified without revealing its discrete components, the universe may have its own pixels of space and time. Below Planck time, the question, what happened before, might be as meaningless as asking what is north of the North Pole. Time as a continuous flow may be just a low-resolution illusion, an approximation that works well in our macroscopic world, but falls apart at its most fundamental structure. This idea forces us to reconsider the nature of the universe. It could be at its core digital, not analog. If the Planck scale shows us the limit of time, the world of quantum mechanics presents us with an even deeper enigma, a place where time seems to lose its leading role entirely. In our everyday world, time is the director of the play. It dictates the sequence, imposes an order, and has a clear arrow pointing from the past to the future. But when we dive into the subatomic realm of particles, this direction and importance dissolve. In the fundamental equations of quantum mechanics, like the Schrödinger equation, time is treated very differently from space. It is not an observable, something that can be measured like a particle's position or momentum. Instead, it functions more like a backdrop, an external and universal parameter that simply moves forward, setting the pace for the evolution of quantum probabilities. There are no clocks within the quantum world. The very laws that govern the behavior of particles are, for the most part, time-symmetric. They work just as well forwards as they do backwards. The real strangeness emerges when physicists try to unify Einstein's general relativity, the theory of the very large, with quantum mechanics, the theory of the very small, to create a theory of everything. In one of the most famous attempts, the Wheeler-DeWitt equation, something astonishing happens. The variable for time t simply disappears from the equation. It cancels out. The equation describes a static, timeless universe, a quantum state of the universe as a whole, where there is no before and no after. It's as if nature, at its most fundamental level, is telling us, time? I don't know what you're talking about. This problem of time is one of the greatest challenges in modern physics. How can time, such a dominant feature of our experience, be absent from our most fundamental theories of reality? The implication is revolutionary. Perhaps time is not a fundamental part of the universe. Perhaps it is an emergent property, something that only appears at larger, more complex scales, like our macroscopic world. Quantum physics leaves us with a dizzying possibility. The flow of time may be an illusion generated by our interaction with a fundamentally timeless universe. After exploring the limits of the very small, let's now expand our view to the cosmos, where Albert Einstein completely revolutionized our understanding of time. Before him, time was seen as a universal river, flowing at the same pace for everyone, everywhere, as imagined by Isaac Newton. Einstein shattered this idea. With his theory of relativity, he demonstrated that time is not absolute. It is elastic, malleable, and intrinsically linked to space, forming a four-dimensional fabric called space-time. In his special relativity, Einstein postulated that the speed of light in a vacuum is the same for all observers, no matter how fast they are moving. For this universal rule to be true, something has to give, and what gives are space and time. The result is time dilation. The faster you move through space, the slower you move through time, relative to a stationary observer. An astronaut traveling near the speed of light would age more slowly than their twin sibling on Earth. For the astronaut, time would pass normally, but upon returning, they would find their sibling much older. Time, therefore, depends on motion. But the revolution didn't stop there. With general relativity, Einstein showed that gravity is not a force, but rather the curvature of the space-time fabric caused by mass and energy. Planets orbit the sun not because they are being pulled, but because they are following straight lines in a curved space-time. And this curvature affects time. Time passes more slowly in stronger gravitational fields. This isn't theory, it's a measurable fact. The atomic clocks on GPS satellites, which are in a weaker gravitational field than we are on the Earth's surface, actually run slightly faster. If engineers didn't correct for this relativistic effect, GPS would be useless. A second on top of a mountain is, in fact, slightly longer than a second at sea level. The consequence of this is reality shattering. There is no universal now. Time is local. Your now is defined by your position and your motion in the cosmos. The now of someone near a black hole, where gravity is extreme, is passing incomparably slower than yours. Time is not the universe's metronome. It is an infinity of local clocks, each ticking at its own pace, shaped by the cosmic dance of matter and energy. The journey we've taken so far leads us to one of the most provocative and profound questions that science and philosophy can ask. What if time is not, in any way, a fundamental feature of the universe? What if it's an illusion, or in more scientific language, an emergent phenomenon? Think about temperature. A single atom has no temperature. Temperature is a property that emerges from the collective motion of many, many atoms. It's a statistical description of a system's behavior. Similarly, a single H2O molecule is not wet. The sensation of wetness emerges from the interaction of billions of these molecules. What if time is like that? At the fundamental level, described by the Wheeler-DeWitt equation, the universe may be a static, timeless block of spacetime, often called the block universe. In this model, the past, present, and future coexist simultaneously, just as all the points on a ruler exist at the same time. The distinction between them would be merely a construct of our consciousness. The now would simply be the point in this block of reality where our consciousness is focused at a given moment. The feeling of the flow of time would be a consequence of the way our brain processes information and constructs memories. We remember the past, but not the future, and this creates the illusion of an arrow of time, a forward motion. In this view, the Big Bang was not a beginning in time, but rather a boundary of time, a point in the block universe. Likewise, the future already exists in this block, not as a predetermined fate, but as part of the four-dimensional tapestry of reality. This idea is profoundly counterintuitive and unsettling. It challenges our most basic experience of life, the feeling of passage. of becoming. But it is a logical possibility that emerges from our current understanding of physics. Time, as we know and feel it, may not be a property of the universe, but rather a property of our perception of it. The universe doesn't have time, we do. Faced with this existential crisis of time, where it seems to dissolve both in the quantum world and in the most comprehensive theories, science has not given up. The idea of a timeless universe is so radical that many physicists are working on alternative theories to try to save time, or at least to understand how it emerges from a more fundamental reality. The fact is that time as we know it is becoming stranger and less fundamental in the models of modern physics. Some theorists, like physicist Carlo Rovelli, propose that time is not a backdrop, but rather a property that emerges from quantum interactions. In loop quantum gravity, space is made of atoms of space, and time arises from the relationship between events, from the change from one quantum state to another. Time would not be a river, but the very sound of the waterfall, the result of interactions. Another powerful candidate to explain the arrow of time is entropy, the second law of thermodynamics. This law states that the total disorder of an isolated system tends to increase over time. The universe began in a state of very low entropy, very ordered at the Big Bang, and has been becoming more and more disordered ever since. Perhaps our perception of the flow of time is just a reflection of this inexorable march toward disorder. We remember the past because it was more ordered, and not the future, which will be more chaotic. Time, in this sense, would be a consequence of thermodynamics, but even these theories do not completely solve the mystery of the now and the subjective experience of flow. Our journey has brought us back to the starting point, but with a new perspective. The second on our clock, defined by the vibrations of a cesium atom, is a triumph of human ingenuity. It is a tool that allows us to build satellites, synchronize the world, and organize our lives. But it is just that, a tool, a ruler to measure something that may not be a line, but a complex web of relationships and perceptions. Time, as we believe it to be, may have never existed. And this realization doesn't have to be frightening. It can be liberating. It completely changes the way we look at life. Because if the flow of time is an illusion constructed by our minds, if the past and future coexist in a way we can barely comprehend, then perhaps the now, this very instant, is all that truly exists and all that truly matters, the only reality we can, in fact, experience. The ticking of the clock continues, but now we hear it differently, not as the beat of a universal master, but as the echo of our own fascinating search for meaning in a mysterious and perhaps timeless universe.